All right, so chapter 7, section 1, the first definition here that will be used throughout the rest of the chapter is a random variable. And a random variable is a numerical outcome of a random process. So think about what the word variable means. And random. And so that's a numerical outcome of a random process. A probability distribution, which we'll go over several types of probability distributions in this chapter, is a model which describes a specific kind of random process. It says it's a model. So, we have to model certain situations with equations in the real world. Have to model certain situations with probabilities. And so it really depends on what type of information we have as to which type of distribution that we use. But a probability distribution is a model which describes a specific kind of random process. Probability distributions are the best descriptors of random processes. For real world random processes, they're kind of hard to obtain for real world use. But people that can do that, that's the people that make the big bucks. You can see listed here, example 7.1 from your book. Probability distribution for the outcome of a coin toss. That one's pretty easy to understand, right? Either you're going to have heads or you're going to have tails. That's the outcome. And then the probability for each is 0.5. So the probability is the same for both of those. It's like that with tossing a coin, with rolling a die, things of that nature. A discrete random variable is a random variable which has a countable number of possible outcomes. Whenever you see the word discrete, you should think countable. So a discrete random variable has a countable number of possible outcomes, like flipping a coin, rolling a die, things of that nature. If you think about rolling a die, not all die, or not all dice, but the ones that we use most commonly with board games, they have 6 sides. And so the random variables would be, what values could X be? 1, 2, 3, 4, 5, and 6. And what's the probability of getting one of these? 1/6 for each one. If we add all those probabilities up, we get 1. Alright, but there's a table that shows the relationship between rolling a die and the probability of getting each number. Your book goes through random phenomenon It says toss a die and observe the outcome of a toss. First, identify the random variable x, the outcome of the toss of a die. Second, the range of values integers must be between 1 and 6. And it says although the value of the random variable is the same as the subscript in this case, there's usually no correlation between the two. The subscript just tells you, this is the first random variable, this is the second random variable, this is the third random variable. And third, the outcome of the toss of a die and their probabilities in the given table. That's what I wrote down there. And the probabilities are deduced using a classical method and the assumption of a fair die. So that's just a probability distribution written in table form. All right, a continuous random variable. So we went over a discrete random variable. A continuous random variable is one that can assume, it is a random variable that can assume any value on a continuous segment of the real number line. So you think about the real number line. We just keep going on and on in both directions to infinity and negative infinity. And so if you have some type of interval on that number line and your random variable can be any value in that given interval on the number line, then it is a continuous random variable. Your book gives an example. It says Cisco's, a local Mexican restaurant, has an express policy that states that lunch will be served within 15 minutes of ordering or it will be free. Obviously, the restaurant is keenly interested in not giving away its product and in delivering on its promise of a timely lunch. But the length of time to prepare each meal varies because of the difference in preparation times of each dish, the load on the kitchen, and the experience of the chefs and waitresses. Since time is measured on a continuous scale, the variability of meal preparation is not predictable, the time between ordering and receiving a meal is considered to be a continuous random variable. Okay, so the random variable is the time between ordering the meal and receiving it. What are the range of values? I guess the range of values would be between 0 and infinity. That's what your book says, because what if they never deliver your meal? Then that's just an infinite amount of time, I guess. But your meal could be delivered at any time, right? More than likely between 0 and 15 minutes. It's not going to be 0, but up to 15 minutes. And it could be any of those values. So that is a continuous random variable. Okay, and that finishes 7.1. 7.2 is on discrete probability distributions. A discrete probability distribution consists of all possible values of the random variable with their associated probabilities. All right. There are two characteristics that discrete probability distributions must have in order to be a probability distribution. The sum of all the probabilities must be equal to 1. Alright, and the probability of any value must be between 0 and 1 inclusively. So it can be 0, it can be 1, and the sum of all the probabilities must be equal to 1. If you think about something that has outcomes, whether it's something as simple as tossing a coin once or tossing a coin 10 times, you know, there are only a finite number of ways all of that can come out. And so if you made a table of those, depending on how many times that you tossed a coin, you could figure out the probability for getting no heads, no tails, you know, one head. Depending on how many times that you tossed the coin, you could fill out a table and figure out all of those probabilities. Well, all of those probabilities will be between 0 and 1. And when you add all those probabilities up, you have to get 1. Okay, they can't add up to be less than 1, they can't add up to be more than 1, they have to be exactly 1. Your book goes through an example of tossing a coin 3 times. And so there's a table, 7.2.1 on tossing a coin 3 times. Alright, and X here in the table is the number of heads in 3 tosses of a coin. So either you're going to have no heads, 1 head, 2 heads, 3 heads, or 4 heads. That's the only outcomes you can have. And notice that the probabilities of getting those aren't the same. Alright? If you write down the sample space for tossing a coin 3 times, there's only 1 out of those 8 times that you could have no heads. So you see beside 0, you have 1/8. And then beside 1, that would be getting 1 head. There's 3 different outcomes that you could have 1 head. So each one of those is 1 out of 8. So it's 1 out of 8 plus 1 out of 8 plus 1 out of 8, or 3/8. The same for 2 heads. Alright, and then for getting 3 heads, there's only one way. If you flip a coin 3 times, that's to get head all 3 times, right? So if you get heads all 3 times, then that's 1/8. Now, notice if you add all of those probabilities together, that you get 1, exactly 1, 1.0. Okay, that's not a coincidence. Alright, your book goes through an example of a computer salesperson that has kept records of computer sales for the last 200 days. It says he recognizes that his daily sales constitute a random process, and he wishes to determine the probability distribution for daily sales. So X, of course, is the number of computers that are sold each day. And you can see in the table listed in the book that he wrote down a frequency distribution. So I guess the sales of 0 computers, 40 days, 1 computer, 20 days, 2 computers, 60 days, and so on and so forth. And then figured out the probability of each of those. Okay? And if we wanted to know, say, the probability that this salesperson is going to sell exactly 3 computers, then it looks like it's 0.2. So that's 20% of the time they will sell exactly 3 computers. Now, what if I wanted to, taking this table, I wanted to know the probability of selling at least 3 computers. So at least 3 computers means the probability of selling 3 computers plus the probability of selling 4 computers, because he never sold more than 4 in a day, right? So that's the largest number, is 4, and that's the largest random variable that we have there as well. And so if you want to know the probability of at least 3 computers, then you write down the probability of 3 computers plus the probability of 4 computers. So that's going to be 0.2 plus 0.2, or 0.4. So 40% of the time on any given day of sales, this salesperson sold at least 3 computers. That's 3 or 4. All right. Pretty easy concept to understand once you get the hang of it. Your book goes through another example on the price of a stock for 30 days. Okay? And where X is the price of the stock 30 days from now. Okay? And then the probability is given for each one of those values. Alright, and then it goes, and so there's a table listed there. You see, that's a probability distribution. You have a copy of this table, but I'm going to put it up here anyway. Okay. So notice that each one of these probabilities is between 0 and 1, and if you add all of the probabilities up, you get exactly 1. I've seen problems where you're given a table and the question is this a probability distribution, or does this describe a probability distribution? And usually, one of the ways that the problem will try to trick you is all of the probabilities won't add up to be 1. Or one of the probabilities will be negative, or one of them will be greater than 1. So we've got to remember that for a probability distribution, the sum of all the probabilities must add up to be 1, and each probability must be between 0 and 1. And it can be 0 or 1, but if it is 1, then that's the only one. Several could be 0, I guess, like the probability of rolling a 7 on a 6-sided die, that's 0. But generally we don't think about things like that. But on this problem, it says an investor has decided that she will purchase the stock if there is at least a 50% chance that the price of the stock will be more than $32 in 30 days. So, at least a 50% chance that the stock will be more than $32 in 30 days. Should the investor purchase the stock? So what we would need to do is sum up the probabilities that are more than 32 days. So you can see that we only have two that are more than 32. There and there. So this is the probability that X is greater than 32. Now it didn't say equal to $32 or more, or it didn't say at least $32. It said more than $32. So we don't include the 32. So this is going to be the probability that X equals 32.5 plus the probability that X equals 33.0. So that's 0.15 plus 0.05, which is 0.2. So the probability that the stock will be more than $32 in 30 days is only 20%. So that would mean that this person would not want to invest in the stock or purchase the stock, because they want at least a 50% chance that the stock will rise. All right. All right, for 32.5, we have 0.15 is the probability that that's what the stock will be after 30 days. And then for 33.0, the probability is 0.05. So all of these values come out of the table that someone else made up about a stock. Okay. So that finishes 7.2.